On the 20th of June 2025, a telescope on a mountain in Chile spent the night taking practice photographs. That's genuinely all it was. Nobody was making a discovery. The observatory wasn't officially open. The people on shift were checking that the mirrors were behaving, that the camera was pointing where the software thought it was pointing, that the whole enormous machine could get through a night without something going wrong. Practice. Homework, basically. And somewhere in the frames from that night, sitting in a crowded patch of sky near the middle of the Milky Way, blended in among 4 background stars, there was a smudge of light that had come from another star system entirely. It had been travelling for something like 10 billion years to be in that particular square of sky on that particular night. And it went completely unnoticed for 10 days. So that's what we're doing for the next couple of hours. 1 photograph and everything that turned out to be inside it. If you fancy sticking around for more of this sort of thing, there's a subscribe button somewhere. Right, let's get into it. The thing sits at 2,682 meters on a peak called Cerro Pachon in northern Chile. And I want to start with the camera because the camera is genuinely silly. It weighs about 6,600 pounds, 3,000 kilos of camera. It has 3,200 megapixels, which is a number that stops meaning anything the second you say it out loud. So let me put it a different way. If you wanted to display a single one of its images at full resolution without losing detail, you'd need something in the region of 400 ultra-high definition televisions arranged into one wall, and it takes one of those images every 30 seconds. All night. Every night. That's the LSST camera, and it's the largest digital camera ever built for astronomy. It sits on the back end of the Simony Survey telescope, which has a primary mirror 8.4 meters across. People keep reaching for the same comparison for the width of the whole assembly, which is a tennis court, and I've never loved that one because a tennis court is flat and this thing is a great big segmented eye pointing upward, but it's roughly right for scale, so we'll allow it. The optics are where it gets clever. Most big telescopes have 2 mirrors. Light comes in, bounces off the big one at the bottom, bounces off a smaller one near the top, goes into the instrument. Rubin has 3, and the properly odd part is that 2 of them are cut from the same piece of glass. The 8.4 meter primary has the 5 meter tertiary mirror sitting in the middle of it, machined out of the same blank, which means the light comes in, hits the outer ring of the big mirror, goes up to the secondary, comes back down into the middle of the same mirror it just bounced off, and then finally goes up into the camera. It's a 3-mirror system that behaves, physically, like 2 objects, and the secondary is the largest convex mirror currently in operation anywhere. The reason for all that trouble is field of view. A normal big telescope sees a keyhole, very deep, very sharp, very small. Rubin sees 9.6 square degrees in a single exposure, which is somewhere around 45 full moons laid out side by side. Depth and width at the same time, which are usually the 2 things you have to trade against each other, and in 30 seconds that combination reaches about magnitude 24. I should explain magnitude briefly because it's one of those systems that seems designed to annoy you. It's backwards. The bigger the number, the fainter the object. It's also logarithmic, so each step of one magnitude is about 2.5 times fainter than the last. The faintest things a properly dark-adapted human eye can pick out on a good night sit around magnitude 6. Magnitude 24 is, very roughly, 16 million times fainter than that. In 30 seconds, half a minute of staring and you're seeing things 16 million times too dim for a person to notice. Then there are the filters. 6 of them, and astronomers being astronomers, they're named U, G, R, I, Z, and Y, which stands for ultraviolet, green, red, infrared, and even more infrared approximately. The camera can swap between them in a couple of minutes using a mechanism that I'm told took years to get right, because you're moving a large piece of expensive glass in front of a larger piece of expensive glass, at speed, in the dark, thousands of times a year, and nobody's there to catch it if it falls. Now, I said the mountain is in Chile, and it's worth talking a bit about why every serious optical telescope built in the last 50 years seems to end up in the same stretch of desert. Northern Chile has 3 things stacked on top of each other that basically don't co-occur anywhere else. It's high, so you're above a chunk of the atmosphere that would otherwise blur your images. It's dry, because the Atacama is one of the driest places on the planet, and water vapor in the air is what smears infrared light into mush. And it's stable, meaning the air flows over those particular peaks smoothly instead of churning. That last one is the real prize. Astronomers call it seeing, and good seeing is worth more than a bigger mirror. You can build a bigger mirror. You can't build calmer air. Here's a fun detail that I think about more than I should. The site is dark enough and the telescope is sensitive enough that satellites are a genuine ongoing engineering problem, not a philosophical one, an actual practical one, where a bright satellite crossing the frame leaves a streak that has to be identified and dealt with in software, on a nightly basis, forever. The team has spent real effort on this. When the observatory was designed in the early 2000s, this was not a thing anybody was planning for. The whole facility cost somewhere around $800 million and took roughly 2 decades from serious concept to first light. That's a long time to work on one thing. There are people who joined the project as postdocs and are now running departments. There's at least one name in the big commissioning papers with a small dagger next to it, and a footnote at the bottom of the page reading author is deceased, which is a phrase that lands differently when you know the project ran for 20 years. People started this and didn't get to see it finish. What it's actually for is the part that I find hardest to hold in my head. It's not a telescope that takes requests. You don't apply for time on it. There's no queue of astronomers with proposals. It just goes. Every clear night it works its way across the southern sky on an automated schedule, and every few nights it's covered the whole thing, and then it starts again. For 10 years. The output isn't a photograph. The output's a film, and that changes what the machine is good for. If you photograph the same patch of sky every 3 nights for a decade, you're not really building a picture of the sky. You're building a record of everything that changed, every asteroid that moved, every star that exploded, every object that brightened, dimmed, wobbled, or wandered across the background. The static universe is almost a side effect. The point is the motion, which is obviously why this whole story exists at all. A single deep photograph of a patch of sky containing a faint smudge tells you almost nothing. A sequence of photographs of the same patch, hours and days apart, tells you the smudge is going somewhere, and once you know it's going somewhere, you can work out where it came from. But we're getting ahead of ourselves, because in June 2025, none of that machinery was switched on. The mirrors were aligned, the camera worked, the telescope pointed. The part of the system that notices things are moving, the part that would have made the whole thing obvious immediately, whereas it wasn't running yet, it couldn't be. It, and the reason why, is one of the better bits of this story, so I'll hold on to it. For now, just the object on the mountain. 3,000 kilos of camera, 8.4 meters of glass, 3 mirrors carved from 2 lumps, sitting at the top of the driest place there is, in air that doesn't move much, taking a photograph every half a minute of a sky that nobody had ever looked at this carefully before. And it's named after a woman who spent most of her career being told she was doing it wrong. She was born Vera Cooper in Philadelphia in 1928, and the family moved to Washington when she was 10, and this is the bit of the story everyone tells, so I'll tell it too, because it's a good bit. Her bedroom window faced north. She could see the stars from her bed, and rather than going to sleep like a sensible child, she'd lie there watching them move. She said later that she found she'd rather watch them than sleep, which, given what this video is, feels like a slightly awkward endorsement, but there you go. Her dad built her a telescope, cardboard tube. She'd already worked out on her own that the whole sky wheels passed overhead in a way you can track, and she'd wondered why the moon appeared to follow the car whenever the family drove anywhere. Those are both, incidentally, the correct questions. She was asking them at about 11, Vassar for the undergraduate degree finishing in 1948, and she picked Vassar partly because Maria Mitchell had taught there, the first professional woman astronomer in America a century earlier. That's a very specific reason to choose a university. Then she wanted Princeton for graduate work, and Princeton didn't admit women to the astronomy program, and would not do so for another 27 years. So she went to Cornell, where her husband Bob was doing a PhD in physical chemistry, and she picked up a master's there in 1951, and then Georgetown for the doctorate, which she finished in 1954 under George Gamow. Gamow, if the name doesn't ring a bell, is one of the 20th century's genuinely enormous physicists. Big Bang cosmology, stellar nucleosynthesis, some of the earliest correct thinking about DNA as a code. He was also, by all accounts, a lot. There's a detail I love here. Georgetown's arrangement at the time meant that when Gamow came to talk to her about her thesis, she wasn't permitted into the room where the discussion would normally happen, so parts of it took place in the corridor. Her master's work, presented at a conference in Ithaca in 1950, argued that galaxies weren't scattered randomly through space, but might be moving in some collective, organised way. She was 22 and pregnant and had a newborn by the time she gave the talk. The reception was chilly. She wrote about it afterwards, and her account is dry in a way I quite admire. She gave her memorised 10-minute talk. She thought it went acceptably, and then one by one a number of angry-sounding men stood up to explain why she couldn't do that. The Associated Press covered it with the line that a young mother had startled the American Astronomical Society. Her thesis a few years later argued that galaxies clump together rather than spreading evenly through the universe, which is now simply how we understand large-scale structure, and which at the time got more or less ignored for 2 decades. She joined the Carnegie Institution's Department of Terrestrial Magnetism in 1965 as its first female staff scientist, and this is where the actual thing happens, because that's where Kent Ford was. Ford had built a spectrograph. Specifically, he'd built one around a new image tube, and the point of it was sensitivity. The claim at the time was that it could improve a telescope's ability to record the spectrum of a faint object by a factor of 10 or more. That's the whole game in observational astronomy. 10 times more sensitive means objects you could never have measured before become measurable in one night instead of never. The story of how they started working together is very good. She turned up for what was essentially an impromptu lunch interview, and somebody handed her one of Ford's photographic plates and asked whether she could measure the stellar velocities of it. She took the plate back to her office at Georgetown and did the work. Under 3 months later, she started the job. She said afterwards that Kent was keen to test the limits of the image tube, and she was keen to get new information about galaxies, which is possibly the most efficient description of a scientific partnership I've ever read. They started on quasars, then she deliberately switched to galaxy rotation, and her stated reason for the switch is something I think about constantly. She wanted a problem she could actually make headway on by going observing, one that people would be interested in, but not so interested that anyone would bother her before she was finished. She chose a quiet corner on purpose. She wanted to be left alone long enough to get it right. So, Andromeda, our nearest big galactic neighbour. The question was simple. How fast do things orbit the centre, and how does that speed change as you move outward? Everyone knew the answer in advance. Look at the solar system. Mercury tears around the sun. Neptune crawls. The further out you go from the mass, the slower things move, because there's less gravity out there holding on to you. A spiral galaxy is a big bright blob of stars in the middle, with thinning arms trailing off. So obviously the stuff in the arms should be moving slower than the stuff near the middle. That's not a theory. That's just Kepler, and Kepler is not up for debate. They went to Kitt Peak in Arizona. Long nights. Ford up on the observing deck taking exposures, Rubin down below developing the plates, and while she waited for them she ate ice cream cones. She could plot the curve as she went. Distance from the centre along one axis, orbital speed up the other, 1 point at a time, cone by cone. 4 cones in, she had a shape. The shape was flat, not gently declining, not a curve that eased off toward the edges the way every textbook and every instinct said it had to. Flat. The gas clouds way out in the sparse outer regions of Andromeda were orbiting at roughly the same speed as the ones near the crowded middle. She said the surprises came very quickly, and that by the end of the first night they were puzzled by the shape of it, and the implication, once you sit with it, is not subtle. If the outer material is moving that fast and the galaxy isn't flying apart, then something is holding it in. Something with a lot of mass, distributed way out beyond where the light stops. Something that pulls exactly like matter and doesn't glow at all. They published Andromeda in 1970, then they did it again, and again. 23 spirals by 1982, and then spirals in clusters after that. Flat, 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 flat. It wasn't a quirk of one galaxy. It was every galaxy. The universe was mostly made of something nobody could see, and the evidence had been sitting in the rotation curves the entire time. She's careful in her own writing, by the way. She never claimed to have discovered dark matter. Fritz Zwicky had suggested something along those lines back in 1933 from the way galaxies moved in the Coma cluster, and had been comprehensively ignored. What Rubin and Ford did was drag the thing out of the realm of one man's odd suggestion, and into a mountain of data so consistent that arguing became embarrassing. That's a different kind of achievement, and I'd argue it's the harder one. She was the first woman to observe with the 5-meter telescope at Palomar. There was no women's toilet in the building. The story that gets passed around is that she cut a paper skirt out of a notebook and stuck it to the little figure on the door, which is either exactly true or has been polished by retelling, and I don't especially want to know which. She got the National Medal of Science, the Royal Astronomical Society's Gold Medal, the Gruber Prize, the Bruce Medal. She did not get a Nobel. She died on Christmas Day, 2016, at 88, and the observatory got her name in 2019. So the largest camera ever built for astronomy, sitting on a mountain staring at a universe we now know is mostly invisible, is named after the person who worked out. It was mostly invisible while eating ice cream and waiting for plates to develop, in a field that spent 30 years telling her she'd got it wrong. No notes, genuinely no notes. Now, let's talk a bit about the party. On the 23rd of June 2025, there was an event in Washington, D.C. where the observatory showed the world what it could do. This is a tradition, and it has a name, First Light, and it's one of the few genuinely ceremonial things left in astronomy. A new telescope opens its eye, takes its first proper look at something, and everyone gathers round to see whether 2 decades of work produced a picture or a very expensive shed. They called this one First Look, and the images had actually been taken weeks earlier, over 9 nights in April and May, mostly pointed at the Virgo cluster. That's a sensible choice. Virgo is a big pile of galaxies about 55 million light-years off, and it's the sort of target where, if your telescope works, you'll know immediately, and if it doesn't, you'll also know immediately. 1,185 frames. Each individual frame reached about magnitude 24, which is roughly what a good existing survey telescope manages and is already deeply impressive. But then they stacked them. Stacking is exactly what it sounds like. You take many photographs of the same patch and add them together, and because the noise in each frame is random and the signal isn't, the noise partially cancels and the faint stuff climbs up out of the murk. Stack all 1,185 and the depth goes to magnitude 26.5, another 10 times fainter than any single frame. What came out of that stack was the picture that went everywhere. 10 million galaxies in one image. Not 10 million stars. Galaxies. Each one 100 billion suns, each one rendered as a little smear of orange or blue or white, a couple of pixels across, and there are 10 million of them, and that's about 0.05% of the galaxies this survey expects to see over its full run. I want to sit on that for a second, because I don't think the framing usually does it justice. When you look at the First Look image, almost every single object in it that isn't obviously a spiky point of light is a galaxy. The background of the picture isn't empty. The background is galaxies. There is no empty. You zoom in on what looks like blank sky, and it fills with more of them, and you zoom in again, and it does it again. And this is one patch. This is a fingernail held at arm's length, more or less. But the bit that genuinely surprised people wasn't the galaxies. It was the rocks. In about 10 hours of test observations, the observatory found 2,104 asteroids nobody had ever seen before. 7 of them near-Earth objects which pose no danger before anyone starts, plus 11 Jupiter Trojans and 9 trans-Neptunian objects out past the big planets. In the same field, it also picked up something like 800 asteroids that were already known and catalogued, for just under 4,000 detections total, meaning the majority of what it found in its own test data had never been found by anybody. For context, and this is the number that does the work, every telescope on Earth and in orbit, all of them together, working all year, find something in the region of 20,000 asteroids annually. This machine, in 10 hours, doing a warm-up, found a tenth of the global annual total. An astrophysicist at Northeastern put it about as plainly as anyone did. He'd expected the galaxies. He knew the galaxies were coming. What surprised him was seeing thousands of asteroids that had never been seen before turn up in a few nights of tests. He said he was not expecting that. The reason it works comes back to the film idea. An asteroid isn't special looking, it's a dot. Everything's a dot. The only thing distinguishing a rock in the asteroid belt from a star 50,000 light-years behind it is that over the course of an hour, the rock moves and the star doesn't. So if you photograph a patch of sky repeatedly and subtract each image from the previous one, everything that stayed still cancels itself out to nothing, and what's left on the page is only the things that changed. The stars vanish. The rocks remain. It's such a simple idea, and it turns an impossibly crowded photograph into an almost empty one, with the answer sitting in the middle of it. There's a video the observatory made from that data, and it's the one thing from first look I'd actually recommend going and finding. It's the 1085 frames played as an animation, and the asteroids come out as coloured tracks, little streaks of orange and green and pink crawling across a background of galaxies that are utterly, completely still. It looks like rain on a window, or midges over a pond in the evening. They're all going different directions at different speeds, and there are thousands of them, and everyone is a lump of rock a few kilometres across that has been quietly going round the sun since before there was anything here to look at it. They also, and I think this is charming, made a version you can listen to. There's a sonification in the Skyviewer app where you drift across the image and the colours and brightnesses of the galaxies get turned into sound, an endless soundscape generated by the actual positions of actual galaxies. It's not science, it's not pretending to be, it's just somebody on the team deciding that people should be able to experience the thing through more than one sense, and I find that quietly lovely. And then there's the follow-up story, which came later, and which I want to mention briefly because it's a good demonstration of how this data works now. A team led by Sarah Greenstreet at the University of Washington went through the first look asteroid detections, looking at how the brightnesses changed over the sequence. An asteroid that tumbles will brighten and dim as different faces catch the sunlight, and the rhythm of that flicker tells you the rotation period. They found 19 that were spinning fast enough to be worth writing a paper about. The quickest of them, a thing called 2025 MN45, completes a full rotation every 1.88 minutes. That's an object roughly twice the height of the Empire State Building turning over completely, end to end, in under 2 minutes. And it's not near Earth, it's out in the main belt, which is unusual for a fast rotator. Greenstreet's suggestion is that it might be a fragment of a long-dead planetary core, smashed apart in some collision in the early solar system, and left spinning ever since. 4.5 billion years of nobody stopping it. I've got a whole thing to say about superfast rotators, honestly, but that's a different video and we'd never get back. The point about first look for our purposes is what it established. On the 23rd of June, the world learned that this telescope could count galaxies by the million and find rocks by the thousand in a single evening's homework. The press coverage was uniformly delighted. Millions of galaxies, thousands of asteroids, the greatest cosmic movie ever made, and so on. And 2 nights before that event, the same telescope had already photographed something considerably stranger than any of it, and nobody in that room in Washington had the faintest idea. Visit 20.25 62000 Nian. Tsuro. Detector 104. 21st of June 2025 at 11 minutes and 32 seconds past 8 in the morning in the timescale astronomers use, which is not the timescale you use, and we'll come back to that because it's funny. That's the file. That's the first image of an interstellar object ever taken by this observatory, and it's got a serial number instead of a name because it was never meant to be anything. The Science Validation Survey, the practice, essentially, the proper structured practice as opposed to the earlier engineering fiddling, began limited operations on the 20th of June, running about half of each night's available telescope time, covering roughly 1,047 square degrees of sky, which sounds enormous, and is actually a fairly compact strip when you consider the whole sky is over 41,000 square degrees. They picked a region along the ecliptic, the plane the planets orbit in, deliberately stretched across a wide range of galactic latitudes so that they'd get both empty fields and horrendously crowded ones, and could find out how the software coped with each. The first night of that survey coincidentally covered the position of the object. The first night, not the third night, not the 10th. The first structured night of the practice survey happened to include the exact square of sky containing the third interstellar object ever detected by humans, which at that moment nobody on Earth knew existed. Here's what was actually in the frame. The object was 4.84 astronomical units from the Sun, call it 720 million kilometres, comfortably out past the asteroid belt, roughly in Jupiter's neighbourhood in terms of distance if not position. It was in Sagittarius. And Sagittarius is where the centre of our galaxy is. which means that particular patch of sky is not so much a field of stars as a wall of them. That matters more than it sounds. Most surveys actively avoid the galactic plane. It's a nightmare. You're trying to measure the brightness and position of one faint dot, and it's sitting in a heaving crowd where every dot overlaps two other dots, and the background isn't dark. It's just a slightly dimmer kind of bright. There's a lovely, weary line in one of the papers about this. The fields were crowded enough that there was effectively no area on the sky without one or more sources in it. There was nowhere to measure the sky from. The sky was full. So the picture, when you finally look at it, is this. There's a cutout, and in the middle of it there's a small, fuzzy thing, and it is nestled. That's the paper's own word, nestled, between four other sources. Three of them are bright enough that the software could tell they were separate objects and pull them apart. The fourth is faint, sits just to the left, and the software never noticed it at all. It's still in there. Its light is still mixed in with the light of the comet, and there's no way to fully get it out, and the team says so plainly in the caption. That's about as honest as scientific writing gets. Here's our measurement, here's the star we couldn't remove from it, do with that what you will. Then there's the 22nd of June, and on that frame there's a rough vertical stripe of saturation masking near the centre. That's what happens when a star is so bright it overwhelms the detector and bleeds up and down the column, and the pipeline blanks out the affected pixels so nobody accidentally measures nonsense. The object isn't inside the masking, it's next to it, just outside the damage. Fine, by luck. The 30th of June is similar. The object is sitting adjacent to a saturated star right at the centre of the frame. Again close, but usable. And then there's the 24th of June, and I have to tell you about the 24th of June because it's my favourite thing in this entire story. The caption in the published paper for panel D reads, "The image was unintentionally out of focus. That's it. That's the whole caption. Somebody was testing something, or a system was mid-adjustment, or the active optics were doing whatever active optics do at 3 a.m, and the telescope took a soft photograph. And there, in the middle of that soft photograph, blurry, is an object from another star system. It has been travelling for something in the order of 10 billion years. It will never come back. And one of the small handful of images that exist of it during that particular fortnight of its life is out of focus, and nobody realised, because nobody knew it was there to focus on. I find that so much more moving than I expected to. Not because it's sad, because it's ordinary. That's how it actually happens. Not a dramatic moment of discovery, not somebody sitting bolt upright at a screen, just a slightly duff frame in a night of test data, sitting on a hard drive for a fortnight. Now, since we're on the subject of the file, let me deal with the time thing because I promised. The timestamp says the 21st of June at 8:11:32, and you might reasonably think that's morning, and that a telescope in Chile taking pictures at 8 in the morning has misunderstood the assignment. It hasn't. That's UTC, more or less, and Chile is 4 hours behind, so locally it's about 4:10 in the morning, middle of the night. Fine. But the actual raw record is in something called TAI, International Atomic Time, which is what the observatory logs in, and which differs from the time on your phone by 37 seconds. The reason is leap seconds. The Earth's rotation is slightly irregular and gradually slowing, so civil time gets a second bunged into it occasionally to keep the clocks lined up with the actual planet. Atomic time doesn't do that. It just counts. It's been counting since 1958 and has never once been corrected for the fact that the planet is a bit wobbly, and the accumulated difference is now 37 seconds and rising. So when you look at that file, the observatory is telling you, to the second, in a timescale that has quietly ignored the Earth's rotation for the better part of 70 years, exactly when the light from an object born before our solar system existed landed on a detector in Chile. And the visit ID starts with 2025 because the night is named for the day it began, so the file thinks it's still the 20th. That's a lot of very precise bookkeeping for a photograph nobody wanted. 9 of those images exist. 9 frames from the serendipitous stretch between the 21st of June and the 2nd of July, where the object simply happened to be in a picture somebody took for another reason. Blended, masked, saturated, blurry. That's the archive. That's what a decade of 10 billion year travel got on the way in. Nobody looked at them for a fortnight. They just sat there on a disk in Chile, filed under the night they were taken, in among a few thousand other frames of a few thousand other bits of sky, being nothing in particular. Atlas is a completely different kind of machine, and I have a lot of time for it. It stands for Asteroid Terrestrial Impact Last Alert System, which is a name reverse-engineered from an acronym, if ever I've heard one, and it's a network of small robotic telescopes. Hawaii, Chile, South Africa. Small, half-metre class. The sort of thing that would be a very nice instrument at a well-funded university and is nothing at all next to an 8.4-metre mirror. But Atlas isn't trying to be deep. Atlas is trying to be everywhere all the time. The job is planetary defence. Sweep the whole visible sky every night or two, looking for anything that's moving and shouldn't be, so that if something is on its way here, we get more than nothing in the way of notice. It's a smoke alarm rather than a microscope. And on the 1st of July 2025, the unit in Rio Hurtado, Chile, which is, and I do enjoy this, about an hour's drive from the mountain we've been talking about, picked up a mover and reported it to the Minor Planet Center. It got a temporary label, A11PL3Z. That's not a name, that's a queue ticket. When something turns up that might be a near-Earth object, it goes onto a page called the NEO confirmation page, with a string like that attached to it, and the string means nothing except, we haven't decided what you are yet. Most of them turn out to be known objects seen from a funny angle, or noise, or a satellite. They get their ticket, they sit on the page, other observers point their telescopes at them, and in a day or two the thing either becomes a real object with a real designation or quietly disappears. The team who found it had, incidentally, drawn one of the harder possible fields. The object was in Sagittarius near the galactic plane, which, as we've established, is the bit of sky most surveys go out of their way to skip. Somebody's software found a moving dot in a wall of stars. That's not nothing. Then the follow-up observations came in, and the orbit fitters got hold of it, and the number that came out of the fit was the number that ends the conversation. Eccentricity of about 6. Right, let me explain that properly, because it's the whole ball game and it deserves a minute. Eccentricity is a measure of how squashed an orbit is. 0 is a perfect circle. Earth's is about 0.007, which is to say very nearly circular. A stretched-out ellipse, a long-period comet swinging in from the outer solar system and back out again, might be 0.9 or 0.99. Halley's is around 0.967. Very stretched, very dramatic, still an ellipse, still a closed loop, still comes back. At exactly 1, the shape stops being a loop. It becomes a parabola, which is the boundary case. The trajectory of an object moving at precisely escape velocity, arriving from infinitely far away with no energy to spare, and leaving again with none. Nothing real sits exactly at 1. Above 1 it's a hyperbola, open, unbound, in one side of the solar system and out the other, once, and gone, and the amount above 1 tells you how much energy it had spare. Now the solar system does occasionally produce mildly hyperbolic objects. A comet gets a gravitational shove off Jupiter on its way past and leaves on a trajectory of 1.01 or 1.01. That's a local object being thrown out of its own house. Those exist. They're not interesting. 6 is not that. 6 means this thing came in at a speed that has nothing to do with the sun's gravity. It means it was already moving, hard, before it ever felt us at all. When it was discovered, still inside Jupiter's orbit, it was doing something like 221,000 kilometers per hour, and at closest approach to the sun, it topped out around 68 kilometers a second. Take the sun's pull out of the sum, and you're left with a leftover speed. Astronomers call it V infinity, the speed it had before it arrived and the speed it'll have again once it's clear of us, of about 58 kilometers per second. There is no mechanism in this solar system for making something do that. It didn't come from here, it came from out there and it was passing through, and the only reason we ever knew about it is that its path happened to cross ours during the 70-odd years in which we've had the ability to notice. On the 2nd of July, the Minor Planet Center made it official. By the time they did, they'd collected 122 observations from 31 different observatories, which is the astronomical community's version of everybody sprinting for the door at once. It got 2 names, C2025N1, which is the comet designation, and means nothing more exciting than the first comet reported in the first half of July 2025, and 3I. 3I is the one that matters. The I series is an entire numbering system, invented from scratch by the International Astronomical Union, for interstellar objects. It exists because in 2017 we found one and realised we had nowhere to put it. It works exactly like you'd hope. They're numbered in order of confirmation. First, second, third. We have needed 3 numbers, ever, in the whole history of the practice. One eye is Oumuamua, October 2017, found by Pan-STARRS in Hawaii, and it caused an enormous fuss because it showed no coma, no visible outgassing, an absurdly extreme light curve suggesting something long and flat and tumbling, and an acceleration that couldn't be fully explained by gravity alone. People are still arguing. Some of that arguing is productive. 2I is Borisov, August 2019, found by an amateur astronomer in Crimea, and this is the detail that always gets me. The third interstellar object humanity ever found was found by a professional survey network built for the job, and the second one was found by a bloke with his own telescope who was looking. Borisov was a proper comet. Coma, tail, the works. Much more carbon monoxide relative to water than our comets have, which was the first real hint that other star systems cook their ices differently to ours. And now, 3I. Third, in 8 years. And 2 of the 3 were found within 2 years of each other, which tells you less about the universe than about us. We only started being able to see them recently. Then came the archaeology, which happened almost immediately and is standard practice. The moment you have an orbit, you can run it backwards and ask every telescope archive on Earth a very specific question. On this date, at this coordinate, were you pointing here? The Zwicky Transient Facility went looking and found the object in data from the 22nd of May, over a month before Atlas reported it. Further digging pushed the earliest recovered image back to the 7th of May, 55 days before discovery. So by mid-July 2025, the picture was roughly this. A third interstellar object confirmed, hyperbolic beyond argument, weakly active, already photographed by several facilities that hadn't noticed at the time, which is a reasonable place for the story to have settled, honestly. Third one found, orbit nailed down, a decent little archive of pre-discovery images from a couple of survey telescopes. Everybody gets on with their summer. That's usually where these things end up. The archaeology went further than the older archives, though, because there was a brand new 8.4-metre telescope in Chile that had spent June taking practice pictures along the ecliptic, and somebody thought it was worth a look. Colin Orion Chandler led that one, University of Washington, and a collaboration called the LSST Interdisciplinary Network for Collaboration and Computing Frameworks, which is a mouthful that exists mostly so it can be shortened. And the first thing to understand about what they did is why it was hard, because on the face of it, this should be trivial. You've got a telescope, you've got the object's orbit, look in the pictures, done. It was not done. Here's the problem, and it's the thing I've been holding on to since the first section. Rubin's ability to find moving objects doesn't come from the telescope. It comes from image differencing, the subtract one picture from another trick that erases everything that stayed still. And to subtract one picture from another, you need the other picture. Specifically, you need what's called a template, a deep, clean, combined image of that exact patch of sky, built from lots of previous visits that represents what the static sky looks like there. In June 2025, for that patch, there were no previous visits. The survey had started on the 20th. There was no history. There was nothing to subtract. The single most powerful moving object detection system ever built was sitting on the mountain with its eyes open, and no memory, and you cannot spot the difference between 2 pictures when you've only ever taken one. So the solar system pipelines weren't running. Not broken. Not switched off out of carelessness. Simply not yet possible, because the observatory hadn't lived long enough to know what the sky was supposed to look like. There's a line in one of the other papers that puts it about as flatly as you can. The lack of previous templates in the region prevented earlier observation and analysis, despite the object being detectable in Rubin images from as early as the 24th of June. Detectable, just not detected. The photons were there. The machinery to notice them was 3 months from existing, which meant Chandler's team couldn't ask the observatory where the object was. They had to tell it. So the approach went like this. They pulled the object's predicted positions from JPL's Scout service. That's the system that generates orbits for things still sitting on the confirmation page, still called A11PL3Z, still officially nothing. Then they went to the exposure table, every image the camera had taken, not just science images, engineering images too, test frames, the lot. For every single one, they asked, at that timestamp, was the object within about 9 degrees of where the telescope was pointing. 9 degrees, because the field of view is enormous, and you'd rather overselect than miss one. Then they refitted the orbit themselves, using software called Layup, and propagated it through every visit again using a survey simulator called Sorcher, cross-checking one method against the other. 2 independent routes to the same list. And when the list came back, they didn't process the images. They processed one chip. I love this bit. The camera has 189 detectors in it, 188 of which are live in a typical visit. It's not one sensor. It's a mosaic, a great tiled wall of them. Calibrating all of that for every frame is expensive in computer time, but if you already know where your object is going to be, to within a fraction of a degree, then you know which single 4000 by 4000 pixel chip it landed on. So they calibrated that one. Just the one. Ignore the other 187, they're not the point. Then they took the raw pixels and did all the unglamorous work by hand. Strip out the instrument signatures, the biases, the darks, the flat fields, all the fingerprints the hardware leaves on every image whether you want them or not. Fit and subtract the sky background. Solve for exactly where the telescope was actually pointing, using the Gaia star catalogue as ground truth, because Gaia has measured 1 billion odd stars to a precision that makes it the reference frame everybody else checks themselves against, and then they had to write their own code. The standard pipeline task for detecting and measuring sources kept falling over in those fields, because the deblender, the software that decides which lumps of light are separate objects, kept hitting blends so large and tangled that it couldn't converge. Too many overlapping stars, it hadn't been tuned for this yet. The paper notes, dryly, that it has since been greatly improved as a result of this work, which is a sentence carrying an enormous amount of somebody's summer inside it. So they wrote a small custom extractor. It takes a 30 by 30 pixel cutout centered on where the object should be, and measures the center of the light in it using a windowed centroid technique borrowed from an old, beloved piece of astronomy software. Then it converts that pixel position into a position on the sky. And then, this is the part that separates real work from a nice story. They checked it. They ran their own code on stars in the same images and compared against the official pipeline's measurements, and got agreement to within about 5 milliseconds. They ran it on known asteroids and compared against JPL's ephemerids. They went and found around 65,000 quasars in Rubin's data and compared their positions against an independent quasar catalogue and got agreement of a couple of milliseconds. They pulled 2.5 million observations of roughly 200,000 known asteroids from the validation data and checked those too, and found a small systematic offset of a few tens of milliseconds. And rather than sweeping it under the rug, they wrote it down, said it was below their noise floor for this object, and left it for a future paper. A millisecond, by the way, is 1/3.6 millionth of a degree. The disagreement they were worried about is roughly the width of a human hair seen from 10 kilometers away. And here's my favourite operational detail of the whole affair. On the 3rd of July, the plan for the night included camera calibration procedures. Routine, boring, necessary. But by then, the discovery had been announced and somebody on shift, the observing specialist, which is the person actually running the telescope that night, knew where the object was, looked at the plan, and moved the telescope. The paper's phrasing is beautiful in its restraint. That sequence was a planned part of test operations for that night, but, noticing the opportunity, the observing specialist shifted the telescope pointing to coincide with the object's position. 32 images came out of that. Combine them, and you get the picture that ended up as Figure 1. 21 30-second exposures in the red filter, stacked, showing the thing properly for the first time. That person is not named. Somewhere in Chile, in the small hours of the 3rd of July, a person doing routine calibration thought, well, while we're here, nudged an $800 million telescope a few degrees sideways, and took the best images anyone had of an interstellar comet at that stage of its approach, and they're an unnamed job title in a caption. I think about that a lot. That's how most good things happen, honestly. It kept going after that. More images through the following week. Then, on the 13th of July, they ran a proper test of the target of opportunity system, the machinery that lets the survey be interrupted mid-schedule when something urgent turns up, which was still being tested and which nobody had had a real reason to use yet. They used the comet as the excuse. Over 35 images, across the full filter set, in one go. The system worked. More frames trickled in over the next week, some deliberate, some accidental again. The last one is the 20th of July. And that's the end of it, and they knew it was the end because they'd run the simulation. Sorsha extended the survey forward using the real observing schedule, including weather losses and maintenance downtime and the shifting geometry, and told them the object would not fall into any further reachable pointings after the 20th. Both methods agreed. Everything recoverable had been recovered. There was nothing left in the archive to find. Which is a strange, quiet thing to be told. The data is complete. Not because you've finished looking, but because there's nothing more to look at. So what was actually in the pictures once they'd been dragged out and cleaned up? Start with the fuzz, because the fuzz is the first real result. A comet is a nucleus, a lump of ice and dust and rock, a few kilometres across at most, surrounded by a coma, which is the cloud of gas and dust boiling off it as it warms. The nucleus is tiny and you basically never see it. What you see is the cloud. They measured how far the light extended from the centre on 2 dates where the object was clear of background stars. On the 21st of June, the coma extended about 6,520 kilometres. 11 days later, on the 2nd of July, about 9,600 sit with those. That's a cloud roughly half the width of the Earth, produced by an object you could walk across in an afternoon, at a distance from the Sun where an ordinary comet would be doing essentially nothing. And in 11 days it grew by about 40%. It was waking up. It had crossed some threshold where the sunlight was finally enough to start driving the ice off, and the cloud was inflating around it like something exhaling very slowly. The team is careful about those numbers, incidentally, and calls them very conservative lower limits, because the object was nearly head-on to us. Anything trailing behind it was pointing more or less away from Earth, hidden in the third dimension where a photograph can't see it. So the real cloud was bigger. We were looking down the barrel. Next, colour. And this is a case where a very unglamorous measurement carries a lot. They measured the difference in brightness between filters. Green minus red came out at 0.657, plus or minus 0.013. Red minus infrared, 0.235. For comparison, they also worked out what the sun's colours would look like in the same filters, because everything out there is just reflecting sunlight, so the sun is your 0 point. Solar green minus red is 0.436, so the object is redder than the sun. Meaningfully, it's not reflecting sunlight neutrally, it's eating the blue end and throwing back the red. That's a familiar signature. Lots of things in the outer solar system are red like this, and the usual explanation involves complex organic molecules built up over long exposure to radiation. Not organic as in alive. Organic as in carbon chemistry, Terry. The sort of thing you get when simple ices sit in the cold and get slowly hammered by cosmic rays for an eternity. It's the colour of stuff that's been left out. Then the light curve, which is where it gets properly odd. On the 3rd of July, thanks to that one observing specialist and their good idea, there were 28 red filter images inside a single hour. That's not archaeology anymore. That's a proper time series. So they could ask, does it flicker? It should. Comets rotate. A nucleus is a lumpy thing, not a sphere, so as it turns, it presents different amounts of surface to the sunlight, and the brightness rises and falls in a rhythm. Measure the rhythm, get the rotation period. That's exactly how they found the fast-spinning asteroid we talked about earlier. They got nothing. They could exclude variation above about 0.1 magnitude across those observations. The best fit for the peak-to-peak variation was 0.014 magnitudes, with an uncertainty of 0.010, which in plain terms means the number is indistinguishable from 0. It didn't flicker. At all. There are 3 ways that happens. 1. The nucleus is nearly spherical, which would be unusual for something that small. 2. We're looking straight down its rotation pole, so it's turning but not showing us any change. 3. And the paper thinks this is most likely. The coma is drowning it out. By that point, the fuzz was contributing so much of the total light that any flicker from the rock inside was simply washed out. You're watching a torch through fog and asking what shape the torch is. There's a nice side effect of that non-result too. The fact that they measured no variability at the Orstron magnitude level, in a horribly crowded field, on a moving target, during commissioning, tells you something good about the camera. Sometimes finding nothing proves the instrument. And now, the tail. Cometary tails point away from the sun. That's the one thing everyone knows about comets, and it's one of the rare bits of common knowledge that's basically correct. It's not about direction of travel. A comet's tail doesn't trail behind it like smoke from a train. It's about radiation pressure. Sunlight physically pushes on dust grains, so the dust gets shoved outward, away from the sun regardless of which way the comet is going. On the way in, the tail is behind it. On the way out, the tail is in front of it. The sun is the only thing that gets a vote. On the 2nd of July, the tail pointed at the sun. The measurement is a position angle of about 290 degrees east of north. That's just a compass bearing drawn on the sky. And the antisolar direction, the way it ought to have gone, was very nearly the opposite. So the first thing you do is check whether you're being fooled by perspective. Because you can be. You're looking at a three-dimensional structure projected flat onto a two-dimensional image, and depending on the viewing geometry, a perfectly ordinary tail pointing away from the sun in space can appear on the sunward side of the nucleus in the picture. That happens. It has a name. It's not exotic. So they modelled it using a technique from 1968 that produces something called a synchrone Sindine grid. The idea is elegant. You simulate dust leaving the nucleus at different times and in different grain sizes, and let gravity and radiation pressure act on it, and then you plot where all that dust should be right now as seen from Earth. Big heavy grains barely feel the sunlight and hang around near the nucleus. Tiny grains get blown away fast. Grains that left a month ago are further along than grains that left yesterday. You end up with a fan of lines showing every place ordinary dust could possibly be. They ran it, assuming dust coming off in all directions equally, which is the standard assumption. The model said the tail should be at about 100 degrees. It was at 290, not near the fan, not on the edge of the fan, nowhere near it, which nominally rules out the perspective explanation and leaves the other one. The dust isn't coming off in all directions. It's coming off in a preferred direction, and that direction happens to be roughly along its path through space and roughly toward the sun. And here's the thing I want to be clear about, because this is exactly the sort of detail that gets grabbed and waved around. This is not unprecedented. The paper names a comet called C2014 UN-271, Bernardinelli Bernstein, an enormous thing from the outer solar system, which showed a similar sunward enhancement, interpreted as large dust grains being ejected slowly and mostly from the sunlit side, which makes intuitive sense. The lit side is the side that's warm. The warm side is the side that's outgassing. If the grains are heavy enough and slow enough, radiation pressure doesn't have time to turn them round before you photograph them. The paper also floats the possibility that it implies a rotation pole lying nearly in the orbital plane, which would tie back neatly to that flat light curve, and then immediately points out that the flat curve could just as easily be the coma smothering everything, so you can't use one to prove the other. And then it does the thing I respect most in the entire document. It says that small cometary nuclei are frequently irregular, often contact binaries, often full of deep concavities perfectly capable of focusing a jet sunward. This was documented in extraordinary detail at Comet 67P by the Rosetta mission, and that without knowing the shape of this nucleus, no firm conclusion on the physical cause can be drawn. Which is to say, we saw something odd, here are 3 good explanations, we can't pick between them, and we're not going to pretend otherwise. That's a tail pointing the wrong way on an object from another star, and the people best placed to sensationalize it wrote a paragraph explaining why they can't. There's a question sitting under all of this that you've probably already asked, and the team asked it too, and then, because they had the tools, they actually answered it properly rather than guessing. Could Rubin have found it first? It saw it first. That's established. The photons landed on the detector 10 days before Atlas reported anything, but seeing and finding are different verbs, and the gap between them is where this whole story lives. So here's how you answer a question like that honestly. You don't reason about it. You simulate it. They took the object's orbit as it was known at the time, along with the uncertainty on that orbit, which comes as a covariance matrix, a mathematical description of how wrong you might be and in which directions. Then they generated 10,000 clones, 10,000 slightly different versions of the object, each one plucked from within the range of what the data allowed. Some a bit faster, some a bit slower, some slightly off to one side. Then they flew all 10,000 through the survey. Not a made-up survey, the real one, the actual pointing history, the actual cadence, with the real weather losses and the real maintenance downtime, and the real changing geometry between the telescope and the object as both moved. and they applied the observatory's genuine criteria for what counts as a discovery. Not, did a photon land on a chip? Did this object meet the standard the pipeline requires to say, that's a new moving thing and here's its orbit? Every single clone got detected, all 10,000. Which isn't surprising when you look at the brightness. The object was around magnitude 18, and the median depth of a single red filter exposure is about 5 magnitudes fainter than that. 5 magnitudes is a factor of about 100. It wasn't near the limit, it was blazing. For 95% of the clones, the first successful observation came on the 21st of June, and discovery came about 13 days later, the 4th of July. Not one clone out of 10,000 was discovered earlier than the 2nd of July. Atlas reported it on the 1st, so there it is. Rubin, running as designed, with everything switched on, would have lost, by days. And the reason isn't sensitivity, it's that discovery takes time. You need multiple detections across multiple nights, linked together, fitted to an orbit that holds up. One dot is not a discovery. One dot is a cosmic ray hit, or a satellite, or noise, or a smudge on a chip. The system deliberately, correctly requires you to see the thing move, several times, over several nights, before it'll say anything out loud. That waiting period is not a flaw. It's the entire reason you can trust the output. And there's a lovely irony in the timing. The survey started on the 20th. The object was in the frame on night 1, so Rubin's clock started the same night the object arrived in its footprint, and the 13 days of linking and confirming would have run out on the 4th, and Atlas, a much smaller telescope that had been running for years and had a warm, mature, fully operational pipeline, got there on the 1st. The paper says it plainly. Had the science validation survey begun 2 weeks earlier, and had the pipelines been running as they will in the full survey, Rubin may indeed have discovered the object first. 2 weeks. That's the margin. 2 weeks of schedule on a project that took 20 years. And if that had happened, it wouldn't be called 3I Atlas. Interstellar objects, like comets, get named for whoever found them. Borisov got the man. Oumuamua broke the pattern because Pan-STARRS wanted something better than a survey acronym and asked for help from Hawaiian language experts, and got a word meaning, roughly, a scout or messenger reaching out from the distant past, which was a good instinct and I'm glad they did it. But the default is the finder, and the finder would have been the observatory, 3I Rubin. I want to be clear that nobody was robbed. Atlas found it fair and square with a smaller telescope in a horrible field, doing exactly the job it was built to do, and that's a genuinely good result for a modest instrument with a practical mission. The Planetary Defense Network spotted the third interstellar object in history. That's a nice day at work, but there's something almost too neat about the alternative. A telescope named for the woman who found the invisible thing by looking harder at data everyone else had already looked at, finding an object from another star in its own practice photographs, and carrying her name out of the solar system attached to it forever. Because that's what would have happened. That name would never have gone away. In 400 years, when the object is somewhere out past the edge of everything and long forgotten by everyone except a database, it would still have been 3I Rubin. It missed by 2 weeks and a piece of software that hadn't finished booting. And what actually did happen is arguably better, in a way I've come round to. The object got found by the smoke alarm. The big new telescope's contribution wasn't the discovery. It was the week and a half beforehand. It was the only deep, high-resolution look anyone will ever get at that object at that distance, on the way in before it warmed up and started performing. Nobody else had an 8-meter class telescope pointed there. Nobody else could have. Those images are unrepeatable, and they exist because the practice schedule happened to include that patch of sky. So Rubin didn't get the name, it got the evidence. And on the balance of things, I suspect the people involved would take the evidence. And there's a small irony in the credit that I enjoy. The network that found it exists for planetary defense. Its entire reason for being is to spot the thing that might hit us, early enough to matter. That's the pitch. That's the funding case. That's what it says on the tin. And the most famous thing it has ever found is an object that was never going to come within twice the distance of the Sun, that posed no threat to anything, and that had nothing whatsoever to do with terrestrial impacts, which is how most surveys earn their keep, honestly. You build a thing to watch for one specific danger, you point it at the whole sky because you have to, and then it finds everything else as a side effect. The rock that might hit us and the visitor from another star look identical through a half-meter telescope. They're both just a dot that moved. You can't build an instrument that only notices the dangerous ones, so the smoke alarm caught it. Fine. That's the system working even if it worked sideways. There's one more wrinkle I can't leave out. There's a paper about the target of opportunity system, the interrupt machinery they tested on the comet in mid-July, and it contains a sentence which, if you've been paying attention, is quietly devastating. Many other science exposures had been obtained before the interrupt was ever triggered, it says, as the object was in the survey footprint for around 2 weeks before its identification. 2 weeks, in the footprint, photographed repeatedly, sitting in the data, unfound. It was never hiding. There was simply nobody home yet. Right, since we've spent this long inside a fortnight in June, let's follow the thing out. And I should be straight with you about something first, because the title of this video is written in the present tense, and the universe has since moved on. When those images were taken, it was inbound. It was coming toward us, in the ordinary sense that its distance from the sun was shrinking, and its distance from Earth was shrinking, and it was day by day getting closer. That was true in June 2025, and it stayed true for months. It isn't true now. It's leaving, and it's been leaving for a while, and it was never going to hit anything. I'd rather tell you that up front than have you sit through 2 hours waiting for a twist that isn't coming. So, the route. It came in from below. That's unusual, and it's worth pausing on. Most things in the solar system live near one flat plane, the ecliptic, because that's where the disk of gas and dust was when everything condensed out of it 4.5 billion years ago. Interstellar objects don't care about our plane. They arrive from wherever they happen to be going. This one came in at an inclination of about 175 degrees, which means it was orbiting the sun almost exactly backwards relative to everything else, and only about 5 degrees off the plane while doing it. Retrograde. Going the wrong way round the roundabout and carrying a great deal more speed than it needed to. Perihelion, closest approach to the sun, was the 29th of October 2025 at about 11:45 in the morning, at a distance of 1.36 astronomical units. That's just inside the orbit of Mars. That number is important for a slightly counterintuitive reason. It never got close to the sun. A properly spectacular comet dives into a fraction of Earth's distance, gets roasted and puts on a show. This one turned round out past us and went home. It got warm, it never got hot. And on the way past, it went near Mars. Not near. The closest the two orbits come is about 0.0018 astronomical units, which is still 2.7 million kilometres. But on the 3rd of October, it was close enough that the fleet of spacecraft we currently have parked at Mars could have a look. Which is a genuinely modern thing to be able to say. There are enough cameras scattered around the solar system now that when something interesting drifts past a planet, we can just ask the local hardware to turn its head. And that's worth dwelling on for a moment because it's a genuinely new capability, and it arrived without anyone announcing it. There is now a permanent distributed accidental observatory, scattered across the inner solar system, orbiters at Mars, spacecraft in transit to Jupiter, missions on their way to asteroids that happen to have a camera, pointed roughly the right way on roughly the right afternoon. Not one of those vehicles was built to look at interstellar comets. Not one of them was designed with this in mind. But they're out there, they've got instruments, and when something drifts through, we can ask. Which means the observation of this object wasn't done by a telescope, it was done by a swarm. Ground-based facilities in Chile and Hawaii and the Canaries and Arizona, space telescopes in orbit around Earth, a solar observatory watching it cross a coronagraph's field, a spacecraft en route to the Trojan asteroids catching it from a couple of 100 million miles off, an ultraviolet instrument at Mars picking out the halo of hydrogen around it. Nobody coordinated that. There's no committee. It's just what happens now when something interesting turns up, and a few hundred people independently think, hang on, I've got an instrument that could see that. I find that quietly one of the most impressive things about the whole business. We have, without particularly meaning to, built a solar system that notices things. Then it went behind the sun. From late October, the geometry was hopeless. The object was on the far side, lost in the glare, and ground-based astrometry simply stopped. That gap is why so much nonsense circulated in that period. There was a fortnight or so where nobody could see it, and the internet decided that must mean something. It came back out in early December, and by the 11th of December it passed less than 2 degrees from the half moon, which is the sort of coincidence that means nothing at all, and is nice anyway. By that point it had swung more than 90 degrees away from the sun, and became observable around midnight. On the 19th of December it made its closest approach to Earth, at about 1.8 astronomical units. That's roughly 270 million kilometres, nearly twice as far away as the sun. That's the whole headed toward us business in numbers. At its absolute closest, this object was almost twice as far from us as the sun is. It was never a near miss. It wasn't a miss. It was a thing that happened in a different part of the room. Opposition, when it was up all night directly opposite the sun from our point of view, which is normally the best possible time to observe something, didn't come until the 22nd of January 2026, and by then it was much fainter, because it had been running away from the sun for 3 months and cooling down and shutting off as it went. That's the frustrating arithmetic of comets. The best viewing geometry arrives after the interesting part is over. Then, Jupiter. On the 16th of March 2026, it passed Jupiter at a distance of about 53.6 million kilometres, and Jupiter's Hill sphere, the region where Jupiter's gravity dominates over the Sun's, the planet's actual sphere of influence, has a radius of about 53.5 million kilometres, so it grazed the edge. It came into almost exactly the boundary of Jupiter's territory and turned away. That's a coincidence, and I want to say that clearly, because it's been made into rather more than a coincidence in some quarters. The Hill radius is not a wall, it's not a membrane, it's a bookkeeping convenience, a rough line where the sums change over from orbiting the Sun to orbiting Jupiter. Something passing near it isn't doing anything except passing, but it did mean ESA's JUICE spacecraft, which is on its long way to Jupiter's icy moons, and happened to be in roughly the right part of space, with roughly the right instruments at roughly the right moment. Gotta look. And the story of that observation is one of my favourite bits of the whole affair, because it's so unglamorous. JUICE had thermal constraints. You can't just point a spacecraft wherever you like. The sun has opinions about which parts of your vehicle are allowed to be warm, so the observation had to be chopped into 6 45-minute windows and one final 4-hour block. That produced 126 science files, about 11 gigabits of data. And then they had to wait. For months. Because JUICE's high-rate radio link wasn't available until the spacecraft entered a cold cruise phase in mid-January, so the data just sat there, aboard a spacecraft, unread, while everybody knew exactly what it was and couldn't have it. The download finally happened on the 17th and 20th of February, in 2 11-hour passes through the deep space antennas at New Norcia in Australia and Malaga in Argentina, 11 hours each, through the night and into the next morning. And there's a note from the flight control team about the moment the signal delay ran out, a 16-minute delay, because that's how far away the spacecraft was, and the first navigation camera images landed in the control room and everyone smiled. That's the job. You take the picture in the autumn, you get it in February, and there's a 16-minute pause before you find out whether it worked. And where is it now? Out past Jupiter, somewhere in Gemini, magnitude 15 and dropping, which puts it out of reach of any backyard telescope and heading fast for out of reach of most professional ones. It never got anywhere near naked eye brightness. It never posed any threat to anything. It came in retrograde from below, went round, and left. And the whole visit, from the first faint recovery detection in early May 2025 to the last useful measurements, gave us an observation arc of about 280 days, out of which the orbit fitters kept 782 observations from a pile of nearly 8,000. 280 days. That's what we get. 10 billion years of travel, and we had it under proper observation for about 9 months, most of which it spent either too far, too close to the sun, or too faint. There's one detail from that first Rubin paper that I like enormously in hindsight. Buried in the discussion, there's a note that the object would become too bright for the camera, actually saturating the detectors, for Rubin to observe it in any filter except possibly the 2 least useful ones, until roughly July 2026, which is now, roughly now. The telescope that saw it first and wasn't allowed to say so has spent the last year unable to look at it, because it was too bright, and is only around about now getting the chance to look again, at a fading dot on its way out of the solar system forever. Here's a thing worth saying out loud before we go any further into this section. Nothing in the Rubin images tells you any of what follows. Not a hint. It was a dot. A slightly fuzzy, slightly red dot, nestled between 4 stars, sometimes out of focus. Everything in this section came from other instruments later, and none of it was predictable from the pictures we've spent an hour and a half discussing, which I think is a useful thing to hold on to, because there's a temptation to treat the first images of something as the important ones, and they're not. They're just the first, right? Size, First, because the size story is a small comedy of its own. Early on, working from pre-covery data before the discovery, one team estimated an upper limit on the nucleus of around 10 kilometres, which raised eyebrows because 10 kilometres is enormous for an interstellar object, and if objects that big are common enough for us to trip over one within 8 years of learning to look, then the galaxy contains far more free-floating mass than anyone can account for. There's a real argument in the literature about exactly that. The mass budget doesn't close. Then the Rubin photometry came in and put the upper limit at 6.6 kilometres, plus or minus half a kilometre, and the authors immediately said they regarded even that as an overestimate, because it depended on how much of the light was coma, and they were fairly sure they'd underestimated the coma. Then Hubble looked, on the 21st of July, and fitted the brightness profile of the inner cloud properly, and got the nucleus down to 2.8 kilometres or less, and then, after perihelion, once the thing had shut off enough to actually be seen, somebody measured it directly, 1.3 kilometres, plus or minus 0.2, 10 to 6.6 to 2.8 to 1.3. Every single time we looked harder it got smaller. That's not a failure. That's exactly what should happen. Every one of those was honestly labelled as an upper limit, and every one of those upper limits held. The object was always a small dirty snowball hiding inside a cloud far bigger than itself, and each better instrument stripped away more of the cloud. It's about the size of a decent English town. That's the thing that's been travelling for 10 billion years, a town's worth of ice, moving at 58 kilometres a second, wearing an atmosphere half the width of the Earth. Now the chemistry, and this is where it stops being a comet story and becomes something else. On the 22nd of June, 2026, 3 weeks ago as I record this, a paper came out in Nature, led by Martin Cordiner at NASA Goddard. They'd used the James Webb Space Telescope's NER-spec instrument on the outbound leg after perihelion, while the coma was still bright enough to analyse and split its light into a high-resolution spectrum. The point of doing that is isotopes, and isotopes are, for my money, the single best trick in this entire field, so let me explain why. Hydrogen normally has one proton and no neutron. Add a neutron and you get deuterium. Chemically it's still hydrogen, it still makes water, but it's twice as heavy, and the ratio of deuterium to ordinary hydrogen in a batch of ice is set by the temperature at which the ice formed. The colder it is, the more deuterium ends up in the water. Below about 30 Kelvin, that's minus 243 Celsius, the chemistry that concentrates heavy hydrogen goes into overdrive, and crucially, once the ice is made, that ratio is locked. There's no process that changes it afterward. So every comet is carrying a thermometer from the day it was born, and the reading is still good billions of years later. They measured it. Roughly 1% of the hydrogen in that water was deuterium, which sounds like nothing. It isn't. Solar system comets sit vastly lower. The measurement is more than an order of magnitude above anything ever seen in a comet from here. The figure that keeps getting quoted is about 30 times. An ALMA team had actually got there first, tracking the signature of heavy water in radio, and found the same thing, and the Webb result confirmed it independently, which is the best kind of confirmation because the two techniques share almost none of the same ways to be wrong. And the carbon does the same thing. They measured carbon-12 against carbon-13 in the carbon dioxide and the carbon monoxide, and the ratios came out higher than typical solar system values. But it's not just that it doesn't match us. Cordiner's line is the one that lands, and he's not being dramatic when he says it. It doesn't match our solar system, it doesn't match our comets, and it doesn't match nearby protostars either. This is something new and different. That last clause is the one that should give you pause. Not matching us is expected, it's from somewhere else. But we can also look at star systems currently forming, the cold clouds, the protoplanetary disks, the places where new comets are being made right now, and it doesn't match those either. So it's not simply a comet from a different address. It's a comet from a different era, made under conditions that don't seem to exist anywhere we can currently point a telescope, hence the age estimates, which are wide and are honestly presented as wide. One team used Gaia's map of how the stars in our galaxy are moving and compared the object's velocity against the known kinematic populations and concluded it's most likely older than 7 billion years, while stressing how uncertain that is. Another put it somewhere in the 3 to 11 billion range. The Webb chemistry pushes toward the upper end. 10 to 12 billion years is the figure being quoted off the isotopes. Our solar system is 4.5 billion years old. The upper end of those estimates puts this object's formation closer to the Big Bang than to us. The same kinematic work also ruled out any shared origin with Oumuamua or Borisov. Different velocities, different histories, 3 unrelated objects from 3 unrelated places. And it noted that this one had an unusually high velocity perpendicular to the galactic plane, which is why it came in from such an odd southerly direction. It wasn't drifting along with the local traffic, it was crossing it. Webb also picked up the organics, methane, methanol, ethane, all clearly present, and nickel vapour, which Cordner flatly couldn't explain. That's the quote. It doesn't make sense to him. Metallic nickel in gas form coming off a lump of ice, at a temperature where nickel has absolutely no business evaporating. There are ideas involving nickel bound up in carbon-bearing compounds that can release it at far lower temperatures than raw metal would need. The honest position is that we don't know. And no, before anyone asks, 5 radio telescopes on 3 continents ran the most sensitive search for artificial signals ever pointed at an object like this, down to power levels that would have caught a mobile phone. Nothing. It's a comet. A very old, very cold, very strange comet, and its strangeness is entirely the sort of strangeness that chemistry produces without help. There's one more consequence, and it's the one I find most quietly enormous. 3 objects. That's the whole sample. Oumuamua was maybe 100 meters. Borisov, maybe 400. Those 2 together suggested a population where small things vastly outnumber large ones, steeply, which fitted neatly with the fact that nobody had ever found one before, because there'd be almost no big ones to find. And then the 3rd one turns up a kilometre and a bit across, and the neat picture stops working. One object doesn't overturn a distribution, but it does disfavour the steep slope, which means either we got extremely lucky, or there are more big ones out there than the first 2 implied, and the galaxy is fuller of this stuff than we thought. There's no way to settle that with 3 data points. You'd need dozens, which is, as it happens, exactly what somebody has just built a telescope to go and get. 9th of June, 2026. A forum post. Not a paper, not a press release. A post on the Rubin Observatory's public community forum which anybody can read, and which mostly contains the sort of thing you'd expect. Questions about data formats, notes about software releases, people asking why a plot looks odd, and a man called Domino Valdano, an independent researcher with a physics PhD and no institution behind him, posts a thread titled Potential Interstellar Visitor, found in April-May 2026, LSST data. And I want to walk through what happens next in some detail, because it is, I think, the single best thing I found while putting this together, and it's got nothing to do with comets. His opening is careful. He says he has some potentially exciting news, and then immediately asks people to verify his data themselves and offer alternative hypotheses or caveats he might be missing in case he's got something wrong. That's the first line. Before the claim, he's already hedging, and it's not false modesty. Read the rest, and it's clear he means it. The work itself is legitimate. Rubin publishes a public alert stream. Every changing thing it sees, streamed out to the world in near real time, and there are brokers, services with names like Fink and Lasserre, that catch that fire hose and let you query it. And within that stream, some detections get linked together by the observatory's own pipeline into known objects, and some don't. The unlinked ones are just orphan dots, a flash of something in a frame, unattached to anything. Valdano took the orphans, and he ran them through a piece of software called Heliolink, a genuinely clever bit of kit whose whole purpose is to take a pile of unrelated dots and work out which ones might be the same object seen on different nights. But he ran it with custom settings, deliberately hunting for hyperbolic solutions, looking for orphan dots that could be strung together into a trajectory that wasn't bound to the sun. And he found one. 9 detections, 3 nights, April the 7th, April the 9th, May the 19th. He labelled it DVAQ1 because it appeared to have come in from the direction of Aquarius. Then he checked it. He refitted the orbit independently with a completely different program, find.orb, which is the standard tool people use for exactly this. Both converged on the same answer. Retrograde, hyperbolic, eccentricity of 10.6, perihelion at 0.387 astronomical units, almost exactly Mercury's distance, and it had gone round the Sun on the 28th of February and had been climbing back out ever since. Mean residual on the fit: 0.2222 arc seconds, and V infinity of about 148 kilometers per second. If that were real, it would be the fastest object ever detected moving through our solar system, by a mile. We talked about 58 for 3i Atlas, and 58 was already remarkable. He wrote up the astrometry properly, in the standard format. He submitted it to the Minor Planet Center the same day. He posted the raw data so anyone could check. He listed 2 further, weaker candidates from the same patch of sky, and explicitly labelled them as lower confidence, for completeness, rather than as anything he believed in. And then he asked for help. He asked whether anyone with access to the images could check for cometary appearance, and whether anyone involved in the observing plan could prioritise a visit to that patch of sky in the coming weeks, because the object was fading and would be lost behind the Sun by August, and if the arc wasn't extended by even one more night of observation, we might never know. That's a good post. That is, by any standard, someone doing the thing correctly. 2 hours and 8 minutes later, Ari Heinze replied, "Research scientist and," this is the part that makes the whole exchange sing, "the author of Heliolink, the man who wrote the software." He opens with an apology for dashing hopes, and then says there is almost no chance it's a real object. And his explanation is the actual content of this section, so here it is. The problem is 3 nights. With only 3 nights of data, it is statistically much easier to fit a spurious orbit to a set of unrelated observations. And yes, any given coincidental alignment is very improbable in itself, but Rubin produces such vast source catalogues that improbable alignments become common, which is a lovely idea when you sit with it. Generate enough data, and the improbable stops being rare. It just turns up, on schedule. Nothing unusual has to happen. You only need enough chances for nothing unusual to happen in a way that looks unusual, and then he gives the number. His team have found hundreds of interstellar linkages that look as good as this one. Hundreds. Most, probably all, must be false, because there's no way that many genuine interstellar objects are passing through at once. They've also found plenty of 3-night linkages with perfectly ordinary orbits, similar spans, similar residuals, which turned out to be 2 unrelated asteroids stitched together by the software into one imaginary object that never existed. So they have rules. 4 nights minimum before they'll submit to the Minor Planet Center. 3-night linkages only when they pass a long list of strict criteria specifically designed to prevent false discoveries. A real interstellar detection would need 4 nights, probably 5. And the residual bar, Rubin's astrometry is so precise that they typically reject anything above 0.20 arcseconds, even for a 4-night linkage on a completely ordinary orbit. Valdano's residual was 0.222, off by 0.02 of an arcsecond. That's the whole difference between worth a look and no. Then a second researcher, Jake Kurlander, adds the piece that turns this from a disappointment into something genuinely fascinating. The parameter space of interstellar orbits is much larger than the parameter space of ordinary asteroid orbits. Think about what that means. An asteroid orbit has to be a closed ellipse of a certain size, in roughly the right plane, going roughly the right way. That's a small box of possibilities. An unbound orbit can be almost anything. Any eccentricity above 1 with no upper limit, any inclination, any speed coming from any direction. It's a vastly bigger box. So if you take a handful of random unrelated dots, and ask the software to find a curve through them, the curve is far more likely to land somewhere in the enormous box than in the small one, which means a surprising fraction of mistakes look interstellar, not because interstellar objects are common, because wrongness is roomier than rightness. That is a genuinely beautiful and slightly unsettling idea, and I've been chewing on it for weeks. The false positives aren't distributed evenly across all the possible answers. They pile up in whichever answer has the most room to be wrong in. And the answer with the most room to be wrong in happens to be the most exciting one. So, how does he take it? He takes it beautifully. He thanks Heinze. He says he was in the middle of composing an email asking for a formal review, and in light of the reply he'll just withdraw the submission rather than waste anyone's time. He says he feels a bit foolish for having posted publicly rather than asking privately first, and then he says he'd been looking forward to thanking Heinze for writing Heliolink if it had turned out to be real. But he supposes he got his hopes up too quickly, and then, and this is the mark of someone actually doing science rather than performing it, he says he's grateful to now know what the bar is. 4 nights under 0.2 arc seconds. He says he'd been wondering why there was no public discussion of any of this, and it's genuinely useful to learn that the team is already actively hunting for hyperbolic candidates. He also makes a fair point in his own defense. If he'd found several of these in his data, he'd have suspected statistics, but this was the only one that stood out, and he was too easily convinced by that. And then the forum does the thing that the internet is not supposed to do. Kurlander tells him he's really glad he brought it up here, that it's a common trap without much public documentation or discussion, and that this is the perfect place for it. Lynn Jones, another member of the team, agrees, says she's glad he posted, because now everyone gets to learn more about how solar system objects are actually being discovered with this data right now, as opposed to in theory, and what the real problems are. Another user goes and independently checks his detections against the broker, finds that the first few belong to 2 different objects with separate identifiers, and posts the link so he can look at the images himself. His response is, "Oh wow, I guess that settles it." Nobody dunked on him. Nobody was smug. A man with no institution made a serious, careful, wrong claim in public, and the people who build the software turned up within 2 hours, explained precisely why it was wrong, thanked him for asking, and turned his mistake into public documentation for everyone else. That's it. That's the section, not the comet. The forum thread. Because remember what we spent the middle of this video on? A team hand calibrating a single chip out of 188 and validating their code against 65,000 quasars to convince themselves that a smudge was where they thought it was. This is the same discipline seen from the other side. That's why the bar is 4 nights. That's why nobody could just look at the June images and announce something. That's why the pipeline waits. The universe is enormous, and the data is enormous, and if you're not extremely careful, it will hand you exactly the answer you were hoping for. 2 weeks ago, this stopped being a story about the past. On the 30th of June 2026, the legacy survey of space and time officially began. 10 years. The whole southern sky, every few nights, for a decade, starting now. It was late, it was supposed to start in early 2026, and the checkouts ran long, which if you followed any large scientific instrument through commissioning, is the least surprising sentence available. And the reason given for the delay is worth reading, because it's a list of the things that actually matter when you're deciding whether a telescope is ready. Jelko Ivesic, who heads the survey, said the decision to officially begin was made after a period of system optimization and a careful operational review of technical readiness, data system performance and scientific validation, and that the factors that played a role included image quality, effective survey speed, system uptime and reliability, and calibration accuracy, which is a funny list to read when you think about what it leaves out. Reliability, uptime, survey speed, not one word about wonder. Those aren't the words of people chasing a beautiful photograph. They're the words of people signing off a factory, and I mean that as a compliment. Nobody needed to check whether it could take a good picture. They'd sorted that a year earlier at the party in Washington. What they needed to know was whether it could take a good picture all night, every night for 10 years, without anybody having to go up the mountain and jiggle something. Because that's the number now. A new image roughly every 40 seconds. 30 seconds of exposure, a few seconds to move and settle and read out, and go again. All night. It doesn't get tired, and it doesn't get bored, and it doesn't have favourites. Bob Bloom, the director, said something in the announcement that I keep coming back to. He said it was amazing and humbling to be there at that time and place after more than 2 decades of work by the team. Which is the sort of thing directors say, but in this case there's a specific weight to it, because we talked earlier about the daggers in the author lists. 2 decades. Some people started this and didn't finish it. Here's what the decade produces, if it all goes to plan. The final dataset will contain billions of objects with trillions of measurements. A deep map with something like 200 million stars in and around our galaxy, and 20 billion distant galaxies in it. In the first year alone, more data than every optical telescope in history put together, and all of it released publicly in regular data releases to anyone who wants it, which is genuinely a first at this scale. There's no priority access. There's no proprietary period where the people who built it get first dibs for a year. The observatory's own line is that Rubin is for everyone. And the alerts. The alert stream went live back in February, and it's the part of this machine I find hardest to sit still about. Every time an image gets subtracted from its template and something has changed, something moved, something brightened, something appeared, something vanished, the system fires off a notification within about a minute to the whole world. The expected volume, once it's fully up to speed, is around 10 million alerts a night. 10 million. Every night. Each one saying, this specific point in the sky is not what it was last time we looked. Obviously no human reads those. Nobody's sitting there. It's brokers, the same sort of services Valdano is pulling from, filtering that torrent down into something a person or a program can act on. This is why that forum thread exists at all. This is the world we're now in. The observatory doesn't find things and announce them. The observatory notices everything that changed and shouts it into the sky. And a global ecosystem of software tries to work out which of the 10 million things mattered. And the moving objects, the estimate is millions of new asteroids within the first 2 years. Millions! Against roughly 20,000 a year for everybody else combined. 2 centuries of asteroid hunting effort, comprehensively lapped in about 24 months. But the number I actually care about, given where we've been for the last 2 hours, is the interstellar one. And the honest answer is a shrug, delivered by a professional. Rosemary Dorsey, who works on exactly this, gave the range as 5 to 500. That's not a hedge. That's a real answer, and the width of it is the information. It could be 5. It could be 500. The reason nobody can narrow it is that it depends on how often planetary systems fling their leftovers out into the galaxy, and we have precisely 3 data points to work from. And as we discussed, the third one broke the pattern the first 2 suggested. So the survey is, among other things, an experiment to find out how full the galaxy is. And the way you run that experiment is, look everywhere, all the time for 10 years, and count. The machinery is ready this time. That's the thing. Everything that wasn't working in June 2025 is working now. There are templates for the whole footprint, so the subtraction has something to subtract against. The solar system pipeline is live, so when a dot moves against the background on several nights, it gets linked into an object and fitted to an orbit automatically. And if that orbit comes back hyperbolic beyond the point of argument, somebody finds out about it that week rather than a fortnight later from a different telescope. And the interrupt system works. The target of opportunity machinery that got its shakedown run on 3i Atlas in July 2025, the one they tested with over 35 images across the filters because they finally had a good enough reason to try it, is now a functioning part of the survey. Which means that if the next one shows up, the telescope can be pulled off its schedule and pointed at it, deliberately, immediately, in every colour it has. That's the difference. Last time the best images we got were an accident, and the best deliberate ones only happened because someone on shift noticed an opportunity during a calibration run and had the confidence to nudge the telescope sideways. Next time, that's a button. There's a page on the observatory's website where you can watch the status of the survey in real time, which patch it's on, what it's doing right now. I'd suggest not looking at it if you have things to do, and it's already started producing the sort of picture that makes the point without any explanation. One of the images from the first nights is a 1.7 gigapixel field of stars in Lupus, which is a fairly unremarkable southern constellation that nobody has ever written a song about. It's just stars. There's no famous nebula in it. It's the sky, photographed properly. That's what 10 years of this looks like. Not a series of triumphs, just the sky, photographed properly, over and over, until everything that ever moves has been caught moving. Somewhere in the frames from tonight, there will be something nobody has any idea about. Statistically, that's just true. With millions of new objects coming, most of tonight's discoveries won't be looked at by a human being for months, if ever. Most of them will be rocks. Some of them will be stars ending. And once every few years, if Dorsey's range lands anywhere near the middle, one of them will have come from somewhere else. The difference is that this time, when it happens, we'll know within about a week. One last detour before we finish, and it's a small one, and it's about the paper itself rather than anything in the sky. I've been saying the team for 2 hours. I should tell you how big the team is. The paper on those images has, depending on exactly how you count, somewhere north of 250 authors. The list runs for pages. Then there's a second list underneath it, of institutions, numbered up past 150. Chile, Washington, Arizona, Princeton, Belfast, Edinburgh, Oxford, Naples, Belgrade, Rijeka, Poznan, Helsinki, Christchurch, Auckland, Santiago, Rio de Janeiro, Curitiba, Kiruna, Ben Guerir, Ann Arbor, Provo, Farmville, Monmouth. There's a company in Bournemouth, there's a bloke trading as his own name in Ontario. There's someone at a Department of Laboratory Medicine in San Francisco, which I assume is a story in itself. And what this enormous international apparatus produced was a paper about a fuzzy dot. I mean that with total affection. That's the whole comedy of modern science, and I think it's rather magnificent. 250 people, 150 institutions, an $800 million telescope, 20 years of construction, and the output is, here is a smudge, here are its coordinates to 70,000ths of an arc second. Here is a star we couldn't quite subtract from it. Here is what colour it is, and here is why we cannot tell you which way its tail is pointing. And I should say, the geography of that list is worth reading on its own. It isn't a list of famous astronomy departments, it's a list of everywhere. There are people in it from countries that have never launched anything and never will, working on the calibration of a camera on a mountain in Chile, and their names sit in the same alphabetical soup as the people at Princeton. There's a line in the observatory's own material about the survey being for everyone, and it's the sort of thing institutions say and don't mean. This lot appear to mean it. The data goes out to the world with no priority window and no favourites, and the paper announcing what the data found has an author list that looks like a phone book for the planet. Now, there's a reason lists get that long, and it isn't vanity. When a facility like this produces a result, the people who built the camera are as responsible for it as the people who measured the dot. So are the people who wrote the calibration software, and the people who worked out how to schedule the observations, and the people who maintain the databases, and the people running the data facility. The measurement isn't separable from the machine. If the mirror is wrong, the number is wrong, so everybody's on it. Which means that buried in that list, in alphabetical chunks, sitting between an astronomer in Warsaw and someone at Brookhaven, are the people who spent a decade making sure a piece of glass was the right shape. They are formally co-discoverers of an interstellar object, because their glass was right. I mentioned the daggers earlier, and I want to come back to them briefly and then leave it alone. Scattered through those author lists are little symbols, and at the bottom of the page there's a key. Most of them are fellowships. This person is a postdoctoral fellow. This person holds a named position. Ordinary bookkeeping, and one of them, a section symbol next to a name in the middle of the list, resolves to 4 words. Author is deceased. That's all it says. No explanation, no elaboration, because a paper isn't the place for one. Somebody worked on this. Somebody was part of the effort that turned a mountain into a telescope, and a telescope into a photograph of an object from another star. And by the time the paper was written, they were gone, and the collaboration did the only thing a collaboration can do, which is keep their name in the list and mark it. I don't want to make more of it than it is. People die. Projects take 20 years, and 20 years is long enough that some of the people who start a thing won't be there at the end of it. And that's true of cathedrals and railways and everything else humans build slowly. But there's a specific thing about a 20-year instrument that I don't think gets said enough. If you join a project like this at 30, you'll be 50 when it produces its first result. That's not a job. That's a substantial fraction of your working life spent on the promise that a machine you can't yet use will one day tell somebody something, and you won't be the one who finds it. The people who find things with this telescope over the next decade will mostly be people who weren't born when it was designed, using data taken by hardware built by strangers, and that's the arrangement, and everyone involved knew it going in. There's something almost agricultural about that. You're not doing the science. You're preparing the ground so that science can happen on it later, at a scale you won't personally see the end of, but it does reframe what you're looking at when you look at that photograph. It's not a picture of a comet. It's a picture of what a few thousand people, over about 2 decades, across dozens of countries in several languages, most of whom have never met each other, can do if they all agree to be careful for long enough, and the object it caught didn't care. That's the part I find genuinely funny rather than sad. It went past at the speed it had always been going, on a trajectory set before the Earth existed, entirely indifferent to whether anyone here had built anything. It was going to sail through the system whether we noticed or not. It has done this before, presumably. It'll be passing other stars long after all of this is dust. We just happened to have finished the telescope in time. Barely. 2 weeks short of finishing it in time properly, but in time. And the paper's own last word on what those images represent is characteristically modest. It says the data illustrate the type of measurements and discoveries the survey will begin to provide once it starts. That's it, that's the claim. Not we caught the great visitor, not our historic first, just this is the sort of thing we'll be doing, routinely, from now on. This will not be remarkable for very long, which is, when you think about it, an extraordinary thing to be able to say about a photograph of an object from another star. So that's the 20th of June 2025, a telescope doing its homework, half a night's worth of practice frames along a strip of the ecliptic, one of them landing on a crowded patch of Sagittarius that most surveys would have skipped. A dot between 4 stars. Nobody watching. Nobody looking. Just a file sitting on a hard drive in Chile being nothing at all for a week and a half, while the object it belonged to carried on falling toward the sun at a speed the sun had nothing to do with. I don't think there's a lesson in it. I've tried to find one and I don't think there is. It's not a story about missing something because nobody missed anything. The system worked exactly as designed, and the design says wait until you're sure, and by the time it would have been sure, a smaller telescope down the road had already said it out loud. It's not a cautionary tale, it's just what actually happened, and what actually happened is slightly funnier and considerably more human than the version where somebody has a moment of genius at a screen. What I keep coming back to is the blurry one, the 24th of June, unintentionally out of focus. Somewhere in an archive there is a soft, slightly wrong photograph of a lump of ancient ice from another star system, taken by the most sophisticated survey telescope ever built, on a night when it was thinking about something else entirely. And the thing is out past Jupiter now, fading, going home. Or going somewhere. It hasn't got a home. It hasn't had one for 10 billion years, and it isn't going to get one. Meanwhile, on the mountain, the survey is running. It started a fortnight ago. It's up there right now, in the dark, in the dry, in air that doesn't move much, working its way across a sky that has never been photographed this carefully. Tonight's frames are being taken as you listen to this. Tomorrow's will be taken tomorrow, and that'll keep happening whether anyone's watching for about 3,500 more nights. Whatever's in them is already in them. Sleep well.